So this is 46. And 46 is x plus 5 over x plus 2 less than 0. Perfect. Okay. So I have x variable in the problem. It doesn't need any preparation because I have a ratio or a product and on one side and 0 on the other. So x plus 5, x plus 2, and the ratio x plus 5 over x plus 2. The variable in the problem can be anything. I need the 0 for this and the 0 for this, so I can put them in the correct order. When is this 0 and when is this 0?
-5 and -2.
That's the correct order. Very good. 0 for this, 0 for this. Now I have to make a decision. When the numerator is 0, what happens to the fraction? When the denominator is 0, what happens to the fraction? When the numerator is 0, in other words, when x is -5, what happens to the fraction? I have to write something here and I have to write something here. And then I can continue. We just had a graph of a rational function, so we know what happens where.
So if -5 is in the numerator, would it just make it 0?
Exactly. Only 0 divided by a number is 0. Very good. What about at -2?
And that one would be undefined?
Indeed. Indeed. Excellent. Both have a positive slope. They look like this. They come from negative, then they're 0, and then they're always positive. They come from negative, then they're 0, and then always positive. I divide two negatives.
Positive.
Good. One negative. No negative. They want negative because only negative is less than 0. Yes, right here. I cannot include either one of them. I cannot include -5 because there is no equal symbol. I can never include -2 because it's undefined. So the answer is open, open, -5, -2. Very good pick. What is left is finding the slant asymptote and the remainder and factor theorem. We went through everything, and I want to mention the intermediate value theorem, as I promised. I didn't forget. I want to add it here. IVT. I'll explain what that is. So we want to look at the slant asymptote. Remainder.
Yes.
Okay. So let's choose one. So we're going back to rational functions. And let me just see the page number. It was 429. Okay, so let's choose a type 2, type 3, and find the slant asymptote. Find the slant asymptote. So these are all type 3. But so is this, 35. And so is this, because the degree of the numerator is exactly by 1 unit higher than the degree of the denominator. So is this. So let's choose any of the type 2. I keep saying type 2. Type 3 that has a slant asymptote, meaning degree of the numerator is by 1 unit higher than the degree of the denominator. And they do not have horizontal asymptotes. Only type 1 and type 2 have horizontal asymptotes. Type 3 does not. It has a slant. So let's choose one. Which number? If you don't choose, I will.
86.
Perfect. 86, f of x equals x squared minus x plus 1 divided by x minus 1. This is indeed type 3. No horizontal asymptote, but slant. This division works with both synthetic as well as long division. Which one would you like to apply?
Synthetic.
Okay. Nothing is missing. They're both in descending order. What goes in the box?
Is it positive 1?
Indeed. And now the coefficients have to be listed even if they don't exist. Degree 2 has coefficient 1. Degree 1 has coefficient -1. No degree has coefficient 1. I always bring down the first coefficient. 1 times 1 is 1. -1 plus 1 is 0. 1 times 0 is 0. 1 plus 0 boxed in as 1. So now, how do I write the answer? I divided degree 2 by degree 1, so this must be degree 1. So this is x, there is nothing else, plus the remainder over the divisor. This is the slant asymptote. That's it. Just the quotient. Y equals x is the slant asymptote. Why just the quotient? Because this piece at infinity will go to 0. It's type 2. This disappears at infinity. Only this one gives us the slant asymptote and the behavior of the function. And since it's a positive x, the behavior of the function is this. So it goes from -infinity to positive infinity following the slant asymptote. That's all you need to find. Other questions, please? Is this okay for the slant asymptote? Going back for a second to quadratics on page 380. I would like to explain a very simple theorem. I wrote 390, of course, called the intermediate value theorem. Use the intermediate value theorem to show that each polynomial has a real solution between the given integers. So, this theorem is valid for functions that are continuous. So, continuous, let me stop for a moment here. Continuous functions. What do we mean by continuous? Well, all polynomials are continuous. No gaps, no vertical asymptotes. So when I graph a polynomial function, I do not lift the marker off the paper. It's a polynomial and it's continuous. So how will a function that is not continuous look like? It has a gap. I had to raise the marker off the paper and start somewhere else. This is not continuous, but this is continuous. So what does this intermediate value theorem, what does it state? Here is what it says. If a function is continuous, and let's say on an interval, a comma b, the function is continuous, and it changes sign at a is negative and at b is positive, there must be a solution between these numbers because it's continuous. It goes, intermediate value theorem, it goes one after the other, one after the other, one after the other, one after the other. It has to go through 0 and then continues to positive. That's all it means. If the function is continuous and it changes sign on an interval, it must have a 0 there. It must have an x-intercept there. That's it. So I like to look at one question here. Use the intermediate value theorem to show that each polynomial has a real solution. And notice something extremely important. All these intervals are 1 unit in length. Not from 0 to 10, not from -5 to 0, not from 2 to 9. No, 1 unit length, from 1 to 2, from 0 to 1, from -1 to 0, from 2 to 3, and so on and so forth. So choose one example. One problem. If not, I will.
We do 35.
Yes, of course, 35. In 35, we're given f of x equals 2x to the 4th minus 4x squared plus 1. And they're giving us the interval -1, 0. Here's what I need to say. F continuous. It's a polynomial as a poly function. Here's what I do next. I find f of -1 and I find f of 0. Of course, with a calculator. F of 0 is very simple, is 1. F of -1 is also simple, but you can put it in the calculator because this is 1 and this is 1. So 2 minus 4 is -2 plus 1 is -1. That's it. So it's a polynomial, it's continuous. At -1, at one end of the interval is negative, at the other end is positive. There must be a solution, at least one solution, or 0, or x-intercept between -1 and 0. Because it's continuous and it changes sign. It's negative at -1 and it's positive at 0. It has to cross the x-axis because it's continuous and it changes sign. That's all. This is it. And the answer is, yes, it does, by IVT, by intermediate value theorem. It does have a solution between -1 and 0 by IVT, intermediate value theorem. That's it. Let's choose one more. Let's say 40. The function is f of x equals 3x cubed minus 8x squared plus x plus 2, and they're telling us between 2 and 3. Okay, so in the graphing calculator, I will erase everything and put in the function 3x cubed and then minus 8x squared, and then plus x plus 2. All I have to do is plug in 2 and 3. If it doesn't change sign, there is no solution, but it does. F of 2 is negative 4, and f of 3 is 14. Therefore, by IVT, there exists at least a solution. Another, or one, at least one, that's better, I'm going to erase that, one solution, or x-intercept in 2 to 3. Guaranteed. Because,
If they were either both negative or both positive, would you just say there's no solution?
yes,
Okay.
yes. If it doesn't change sign on this interval, then there is no solution. Yep. Very good. So the last one that we haven't looked at, so even the slant asymptote was done, even the IVT. I will not put an IVT on the, I just want you to know it's a very simple theorem, but I will not put it on the on this test or on a test or final, no. I just want you to know about this very simple theorem. So the only thing that is a remainder here is the remainder and the factor theorem. And they are in 3.3 in the dividing polynomials, and they are on page 395. There is really nothing else to look at. Okay, using syntactic division and the remainder theorem to find the indicated function value. So that's one thing, which is the same with the remainder and the factor theorem. The same thing. So my question that I am going to ask you to work on the test is something like is f of x divisible? In other words, does it have a factor by, let's say, x plus 3? And let's say f of x equals x cubed minus 3x plus 9. In other words, I'm asking, and part A will be use remainder theorem. So the remainder theorem says that if I have this f of x divided by x plus 3, the remainder of this is f of negative 3. If f of negative 3, I don't know, I didn't calculate anything, but if f of negative 3 is 0, then in part B, I will ask, is x plus 3 a factor of f of x? And you will say yes, because the remainder is 0. Or you will say no, because the remainder is not 0. That's it. So I'll put the function, plug in negative 3. I'll put in the calculator, plug in negative 3, and immediately make a decision. So here's the function. Clear? I just made it up on the spot. Minus 3x and plus 9. I will evaluate it at -3. The answer is -9. It's not 0. The answer is -9. And I will say no. Since the remainder is -9. That's it. Use the remainder theorem to identify the remainder. Fine. I plug in f, I plug in -3. If I have x minus 4, I plug in 4. If I have x plus 11, I plug in -11. Calculate. The remainder is -9. No, x plus 3 is not a factor of f of x because the remainder is not 0. By the remainder theorem, I found it. The remainder is -9. It's not a factor. If the remainder is 0 or were 0, then I would say yes, since the remainder is 0. This is it. There is really nothing else. These are all the topics we discussed in chapter 3. Any questions?